Today I'm going to talk to you about preservation and survivorship potential of soft-bodied organisms in sediment-density flows. Yes. So today I want to address to you two main questions here, which is one, what are the effects of different sediment density flows and durations on soft-bodied organisms? And secondly, what implications does this have then for fossil assemblages such as the Burgess Shale? So to try and address the first question, I conducted a series of experiments and I tested durability and preservation potential. And this was a 3-factorial design where I used freshly killed specimens of polychaetes, invertebrates, elitevirans, and I have a dependent variable of indices of bodily damage, which I'll explain to you momentarily. And I have 3 independent variables. So these are 3 factors in a sediment density flow that I want to see whether they're causing effective damage on soft-bodied animals. So first is flow duration. So I decided this one, obviously the longer something stays in a flow, you suspect that you would see more damage. So for this you go from 5 minutes and then the longest experiment ran for 180 minutes. Second is sediment concentration. So for this I have 3 parameters. 0%, which is the control, so that's no sediment in the annular flume tank. 5%, which is a dilute concentrated sediment density flow, and 10%, which is a dense concentrated sediment density flow. So what you would hope to observe here is that at the higher concentrations you get more grain-on-grain impact occurring, and therefore hopefully more grains damaging the polychaetes. And thirdly, grain texture, which is angularity. I have rounded grains and then angular grains, which again, the higher you increase your angularity, the more increase on damage state. So I did 5 replicates of different combinations of these with 125 experiments to do. So first of all, how do I quantify state of damage on freshly killed invertebrates? So for this I devised an index of bodily damage, as I said. And what you see is the polychaete, once it's freshly euthanized, it goes through a series of damage states. So you start off at 1, which is when it's just been killed and it's undamaged, and then you end up at state 6 when it becomes fragmented and the body splits into 2 or more pieces. And during the time in the tank, depending on what time to take it out, it might go through a series of these states where you get swelling in the parapodia, you get rupturing along the cuticle, and then you get more severe swelling and sort of blistering happening as well. So that's how I'm able to quantify when it comes out of the experiment, I can observe the amount of damage externally on the polychaete. So for anyone of you who don't understand what an annular flume tank is, so it's able to replicate boundary layer conditions of a turbidity current or sediment density flows. This is what it looks like in the ocean, and this is what it looks like in the lab. So it's a ring-shaped channel. It's at 3.9 meters per second to produce the turbulence. And I have grain size of 75 to 250 microns, which is small to medium size sand grade. And you have 160 litres of artificial seawater in there. So the polychaete's going through a pretty rough time in that. And the reason why the base counter-rotates those paddles on the top is then I can reduce secondary circulation happening in the tank and then to form a continuous straight flow. So results. I formed an ordinal logistic regression to see any overall significance within the data, which was great. And then I formed some post-hoc Prestel-Wallace tests. So first off, flow duration. Yes, it is statistically significant. From these graphs here, you can see that basically when you put it in at 5 minutes, it comes out at state 1. And when it's up to 180 minutes, you get the most damage seen. Interestingly, the only one that actually didn't come out statistically significant is when you have a combination of 10% sediment with your angular sediment. And what's happening here is, you have here is at 5 minutes, you have them at state 1, and then you have this really increasing gradient and it plateaus here where everything is getting highly damaged in that 10% concentration with angular sediment. Secondly then is sediment concentration. Sediment concentration actually didn't have an overall significant effect. However, if you actually separate out your angular grains from your rounded grains, you find that rounded grains have absolutely no significance, but angular does become significant. And then thirdly is grain angularity. So grain angularity, as we would expect, the angular grains come out as statistically significant, and your rounded grains don't come out at all as significant. So Moving on, going back into the Cambrian now, to explain a bit more about another part of my project, is trying to understand more about the Burgess Shale, which we all know is set back in the Cambrian, just after the Cambrian explosion. It holds key insights into early soft-bodied evolution, and there's still this ongoing sort of debate, these two hypotheses of how these animals got preserved and were they living in the environment that they're deposited in. So on one side of that debate we have people who think they're distal turbidity currents, where the animals get caught up in a cloud of sediment and they're transported down into the anoxic sediment that they're preserved in. And then you have other people who think that it was minimal transport due to the degree of articulation. They think that transport had to be minimal, or they were living within the environment that they're found in. So in order to collect data and to try and test these hypotheses, I first went out to the Burgess Shale, equipped with some bear spray, which you can see there. Some nice camping sites. And I visited these three localities, which was the Walcott Quarry on your far left. In the middle is the Raymond Quarry, which is situated just above the Walcott Quarry. And then Stanley Glacier site, which is located in a different national park. So in order to try and understand the characteristics of the sedimentary features across the sequence, this is why I went to a number of localities to collect data from each of them. And then I can feed these kind of sedimentary structures back into my experimental design. So what I did was I collected grain size analysis, I did sedimentary logs, and I looked at the sedimentary structures. So what we see here is, interestingly, you get in your Stephen Formation, which is in the Stanley Glacier, you get an abundance of trace fossils. So you can see little traces here. Then you get absolutely none in the Walcott Quarry, as most of you are aware. But you get these big clusters of, quartz grains, and then you get these scour marks here, on a millimetre size scale, as well as getting other scour marks here, much larger scale at Stanley Glacier site. And then again in the Walcott Quarry you have another sort of centimetre scale scour, and that's infilled then with shelly debris. So these sort of sedimentary features, along with other features, can then help me interpret flow dynamics. And then I can sort of develop the boundary layer conditions of the Burgess Shale and then replicate them again in my experiments that I showed you previously. So just to finish up on the Burgess Shale piece, yes, it's a beautiful place, and the 3-hour hike, it's probably worth it for this view here, and that's the phyllopod bed there in the Walcott Quarry. So I'm going to bring you back into the present now and talk to you about some sort of accidental experiments I ended up doing. And this is, what is the survivorship potential and viability of a polychaete after being subjected to a turbulent flow? And secondly, just how functional is an organism after coming out of the flow if you put it in alive? So I ended up doing these because I euthanized a polychaete in one of my preliminary experiments. I put him into the tank, I spun him around for 3 hours at 3.9 meters per second, and I took him out, and he was alive. So that wasn't supposed to happen. So then that got me thinking, well, if this guy can survive, what if I go and torture some more polychaetes and put them into the tank and see what happens? So that's kind of where these two questions sort of came up out of. And this is sort of based around this doomed pioneer hypothesis, which basically is when you get animals like crustaceans, this little guy here, what's going on? And comes up and he's living in a relatively shallow marine environment, and he gets transported by a sediment density flow into an anoxic one. So that's going to have problems. You're getting an alloctonous organism making in situ traces in anoxic sediment, not where it's supposed to be. And then it eventually dies after a number of days. But what I want to know is, well, can this actually happen? So for this, again, I went back into the lab to do more experiments. I did a matched pairs design. This time you have a dependent variable, which is your time taken to burrow, and then your independent variables, which is when I have an untransported polychaete, and I compare that time taken to burrow compared to the transported one. So this is what it looks like in the lab. I look slightly insane. You get a happy polychaete in the tank. He doesn't know, unaware of what's about to happen. Then you spin him around for 3 hours at 2.9 meters per second. And then you check its quantified state of damage again. This one's really annoyed at me. He he won't stay still either, try and take a picture. And then you put him into one of these tanks here. At the same time, I put in one that hasn't been transported, so he's the lucky one. You put them in at the same time, and then you calculate the time taken to burrow. And this is what you see here. So, to answer your question, yes, they can burrow after being transported, and yes, they can make traces quite easily, and they move around quite a lot. So, I think he's just trying to escape me. So, results from these experiments. Time taken to burrow. So, you can see here, this is your untransported polychaetes. They take on average 8 minutes to burrow into the anoxic sediment. And then you get transported polychaetes taking twice as long, 16 minutes. And of course, this then comes out as statistically significant. And then interestingly then, you can see their burrows. So what happens here, you have the transported versus the untransported. And what you see is, yes, they can make deep U-shaped burrows, they're making shallow ones here. But then interestingly, you have the transported polychaetes. Their posterior region, at times, they burrow for a certain amount of time, and then their posterior region just stays at the sediment-water interface. And it's either, I could put it down to two things, it's become disorientated from the experiment, and it can't really remember what it's supposed to be doing, or secondly, the posterior region's actually become damaged, and it's no longer able to actually use this part of its body to burrow into the sediment. So that was pretty interesting. So to sum up then, yes, I still have to do Burgess shale flow conditions in my lab once I have the rest of my data analysed. Then I have further dune pioneer experiments where I'm going to actually leave them in sometimes for a while to see what are they able to do if I leave them in the anoxic sediment for up to a number of days. Do they eventually expire? Or can they make sort of networks of burrows and not just simple U-shaped ones? And then thirdly, yes, I will be using other invertebrates, so I'll be using arthropods, probably shrimp as well, to represent a larger proportion of the Burgess shale as well. So I just want to thank you again for listening, and thank you to my supervisors who were great in the field. So thanks very much.